Hi, everyone. Thanks for joining us today for our chemistry webinar. We'll be getting started here in just a moment or two, give people a chance to join us here on the Zoom call. Just to go over a few housekeeping items before we get started. Wanted to let you know that we would love to answer your questions throughout today's webinar. So feel free to use the Q&A or the chat feature. We'll be monitoring both of those. We're going to do our best to answer all of the questions today, but if we happen to not get to your question, we'll definitely be following up with you after today's webinar. I'll also be sharing a link to a shared Google folder that has lots of great resources for you that your presenter, News, has put together, some data files, and then more details about the experiments that he's going to be going over today. I'll also be letting you know where you can find the recording. We are recording this webinar and it will be available for you to view in a few days, probably later this week. And I'll share where you can find that on our website closer to the end of today's session. So I will introduce you real quickly. I'll introduce you to Melissa Hill, who is going to be in the background helping to answer your questions. She's one of our chemistry experts, so she'll be helping with those technical questions. And then I'll be introducing News, who's going to be your main presenter, and we'll go over his bio here in a moment. So whenever you're ready, News, to start the presentation, feel free.
All right, here we go. All right, there we go. Give me a sec here and I'll get it the right way. All right, there you go.
Perfect. Okay, so welcome again to the webinar, Exploring Chemistry Through Hands-On Experimentation. You can go to the next. And so today's agenda, we're going to be going over the gas laws in a jiffy experiment, and then the kinetics of food dyes. We'll also be, or News will be talking more about remote education for different scenarios. If you're in the classroom, have a hybrid in and outside the classroom, or completely remote. And then he'll be going over the hands-on demonstration of both of those experiments I just talked about. We'll have time for Q&A, but again, we encourage you to put those questions in either the Q&A or the chat during the session, and we'd love to answer those for you during the session. And then I'll be letting you know where you can find the recording. You can go to the next slide, News. So more about your presenter, News Hissam. He has 34 years of high school chemistry and physics teacher experience in Frederick County, Maryland. He's a 1991 Presidential Award for Excellence in Mathematics and Science Teaching for the state of Maryland. And he's a National Board for Professional Teaching Standards teacher since 2001. He's been using Vernier equipment for a long time and consulting since 1984. He has many national presentations and workshops that he has done, and he has 5 years at Vernier doing faculty training, webinars similar to this, curriculum development, and he is part of our technical support team in our chemistry department. So we're here for you again. We want you to be able to ask and have us answer your questions, so feel free to put those in the Q&A and the chat. We will be going over, and News will be showing you more about our graphical analysis app. So he will be doing some hands-on activities. If you haven't had a chance to download graphical analysis, I'll put the link where you can do that in the chat in a moment. And I'm going to pass it over to News.
All right, let's talk a little bit about remote education, which none of us at Vernier ever had to do when we were in the classroom. So the challenge for Vernier was to try to come up with a way to help support teachers with this tremendously challenging thing. I've been talking to a number of my colleagues that are still in the classroom, and we understand that this has been a real tough time for you folks. And so from Vernier's point of view, what can we do to help support teachers? So we have a bunch of remote solutions on our website. We posted sample data, and we have some videos, and a lot of teachers were wondering about, like, is there a way that we could like collect the data but also show the show the students while we're doing that? And that's what today is all about, is showing how you can do that, and you can continue to do this even after these crazy days. Maybe a student is sick and home, but not so bad that they can, at least watch and participate. That's what's going to happen today. So if you want to do that with me, then you can be the student, I'll be the teacher. Get a copy of graphical analysis on your device, doesn't matter what. Could be a phone, a tablet, a Chromebook, anything, computer. But if you don't already have it, make sure that you get a copy of graphical analysis and put that on your device. The code down there we're going to use in just a few minutes. And so the way you can use graphical analysis in your classroom is multiple ways. Like, what you can do is, if a student's right there in the room with you, you could share the data right there. And it's not, you're not limited to this. I mean, you could have one student collecting data and sharing their data with other students. I mean, that's also a possibility. So a group could be collecting data and everyone in the group pulling down their own copy of the data. But a student could be at home or some other location. And so with the hybrid classrooms that we've been hearing about here at Vernier, instead of doing labs twice, I have a friend in New Jersey who did exactly this, where he had students at school transmitting their data to their lab partners at home. Or it's possible that you can set graphical analysis up, data files up with videos and store data, and students can analyze the data on their own. So there's lots of ways that you can use this setup to enhance your instruction. And I hope that you'll see that today. I was thinking about, like, what sorts of things would people like to do, and temperature labs that use time-based are very obvious. So I was thinking, what about something different? This gas laws lab, last time I did an NSTA, boy, the teachers really liked it, and I thought, let me see if I can share that with you all. So that's what we're going to do, is we're going to look at gas laws. I'm going to look at Charles law and Gay-Lussac's law. If we have time, I have an hour, so if we have time, we might try to slip a little bit of Avogadro in there, but we'll have to see. And then I'd like to do a time-based experiment. It's going to be exactly the same procedure as crystal violet, but I'm going to use blue food dye to do that. So let's do this, okay? So I'm the teacher. So here is my copy of graphical analysis. Let me get it up here so you guys can see it. And now this is my student computer. And if you have graphical analysis on your device, pull it up. And if you don't have a Pro, if you have Pro already, wait for a second, because I'm assuming that you don't have Pro. We're going to make everybody's copy of graphical analysis Pro right now. And so here's how you do it. Okay, and you can follow along. I've got my iPad sitting right here, and so that's what you're seeing on the right side, and the left side is my teacher computer. If you look at the top of the screen, you'll see the thing that looks like a shield. Okay, so if you've started up graphical analysis, you might have a screen that looks like this. If you X out of this temporarily right now, and you'll get a screen that looks like that. Here, let me do my student screen. So there's my student screen. Tap on the shield, okay? And you're gonna get a box that looks like that. Let me do it on my iPad. So there's the box. And Angie, if you wouldn't mind pasting that code in, this code down here, when you buy Graphical Analysis Pro from us, which is a subscription, you pay an annual fee for Graphical Analysis Pro, but you will get a code similar to this. And what you need to do is enter that code exactly. You can copy and paste it, or if you're on a portable device, you may have to type it in, but you only do this once. Okay, so once you have put that code in, you should be golden. Okay, so you just want to make sure that if you can copy and paste it, it's great. on, a device like my iPad here, I can't really do that. So I've got to do, and you got to be careful. Caps matter, because I mean, it's what it is, right? So you got to, make sure that you put the codes in just exactly right. So let's get the W lowercase, and we'll talk about some other codes later on. There's only one other one that we're going to deal with, and you'll see that in a bit. So what you're doing here is you're converting your copy of graphical analysis to Pro. So submit that. I'll submit this. Maybe I'll submit that. There we go. And what you've just done, if everything has worked the way I hope it has for you, notice that my teacher view and my student view are telling me I've got 14 days for this code, and you guys are welcome to use this code all you want for the next 2 weeks. We do have a free 30-day preview that Angie's going to tell you about, or we're going to look at the end, where you can download it. You can set up yourself for 30 days. You might want to wait to request that for a couple of weeks, but we're ready to go. We're all set. Now, here's what I'd like you to do right now. I'm going to set up an experiment. I'm going to share it with you. You're going to see it. And you're going to pull the data down on your computer. So right now, or your device, what I'd like you to do is right up here where it says untitled in the top left, what I would like you to do is tap on that and do a new experiment. Okay, so you should have a screen that looks like this. You are not collecting data. I am. So what I need you to do is tap where it says data sharing, and then I need you to take a sip of coffee and just wait for a second. Okay, just wait, because this next code is something we'll talk about. I'm the teacher. I need to set up the experiment so I can share it with my students. So what am I doing? Let me show you what I'm doing. Okay, this is my lab right here. So this is, let me put my hand in here so you can see that this is real. And what we're going to do is we're going to do the Gay-Lussac's experiment. We're going to take we're going to measure the pressure and the temperature of the gas in this flask, and we're going to plot that at different temperatures. And for today's purposes, I've got 3 water baths. I've got a real cold one, a room temperature one, and a warm one. And that's all we're going to do. In the real experiment, we would do five data baths, but for our purposes, because time is short, we're just going to do 3. So I'm going to set up this experiment. And I'll do a new experiment. You just watch for now. Don't get too excited. Just watch. I'm the teacher. I'm connecting my sensors. So with these Go Direct sensors, you need to push a little button on there. You may see on the camera that the light is flashing. That's indicating that these sensors are ready to connect. So let's see, I have a temperature sensor. So, oh, there it is, G5. Let me connect to that guy. Every sensor has an ID, has a unique code. So if you got a whole bunch of these in your classroom, the kids would just look at the code on the side of the sensor. Okay, so that's cool. I've got that set up. Hey, Noose. We don't want time, we want pressure and temperature. Oh, okay. So we don't need 2 graphs. I'm going to set this up for 1 graph. Okay. And we're going to do pressure on the, whoops, got to flip it this way. We're going to do temperature. Temperature will be our independent variable. Pressure will be our dependent variable. So to change what's plotted on the axes, you tap on the variables. Now, the other thing that we need to do is we need to change the way data is collected. By the way, teachers, pro tip, Melissa showed me this. Tap on the 3 dots, go to presentation, and you can blow up your screen a little bit so it's easier for folks to see what you're doing. This is great in a classroom, right? Another nice little tool, make things a little bit bigger. So anyway, I want to do what's known as events-based data collection. So time doesn't work here. So I'm going to tap at the bottom left, and I'm going to change the mode of data collection. Right now it defaults to time, but I want event-based. We can measure both of these parameters with sensors. So I'm going to use selected events. Now, sometimes the parameters will vary slightly over time. And so we have this option to average the readings. Sometimes that's a nice one to turn on. I want you to see what that looks like. Let me hit done. Okay. And I am ready. notice that I've got my experiment set up. Oh, look, my axes changed. Oh, that's annoying. Let's go back and fix those. Temperature on the X, because that's the dependent variable, pressure on the Y, that's the pardon me, I said that backwards, didn't I? The temperature is the independent variable, and pressure is the dependent variable. Hey, Noose, wouldn't it be nice if I could make these meters bigger? Yeah, let's do that. This top box here, box in the boxes, it's a view option. I can turn meters on, and that makes it nice. These little ones are still working, but kind of nice. I'm ready to start collecting data. I'm ready to share with you. So here's how you do it. All your students have GA Pro now. And so I'm going to tap on the TIE Fighter. Oh, look, the shield turned into a TIE Fighter. Isn't that cool? I don't know. Dave thinks it looks like like sound waves, but I think it's better to call it a TIE Fighter. Now I'm the teacher. You don't do this. Watch what happens. I'm going to tap there and I'm going to start a new session. And this is where you need to pay attention. Sorry, students, you now need to pay attention. Okay, so check out this code. This is my what you're looking at on the right here is my iPad. You need to type that code, or I can also copy and paste it into the chat. But honestly, this is an easy one. What we had the programmers do is make it so that it's a little easier to type in. And so with, knowing that you're on a phone and you don't want to be screwing around with caps and those O's and, all the weird letters that are just, so they programmed it pretty well so that when you type those codes in, it's relatively, you're less likely to goof up. Hey, Noose, you have all these meters and cool things on your screen. I don't have that, but I want you to notice something. Bottom left corner, my iPad says data share. Does your device say data share? Okay. By the way, you can internet crickets, or you can send us a chat and say, yeah, I've got data share, but it's not, doesn't look like mine. So what you can do is on your device, we are only going to send you raw data. Students are on their own to adjust things like tables and meters and things like that. So you'll notice now in my iPad, those are all set. But I did that on my iPad. So that would be the student on their end, okay, doing those sorts of things. I'm just going to send you data. So, all right. So I'm ready to send data. Here we go. Let's collect data. We are in events-based data collection, zero anxiety. Let me put the camera up here. So I have my super duper cold water bath here. Well, I don't know, super duper cold. Notice the way I'm holding the flask. Little bit unusual. Also, notice the high-tech, super expensive beakers that I'm using. Of course, in Oregon, we get to pay 10 cents a piece for those. Okay, but check it out. Talk about getting that flask all the way submerged into that. If I had clamped that flask right at the neck of the flask, I wouldn't have been able to submerge it completely. And I found you get better data if you can completely submerge the flask. So now ideally, what I should do is wait 3 to 5 minutes, because the water, the specific, the thermal, what do you call it, conductivity of the glass and the air. Yeah, I've got 42 minutes left in this webinar. So I'm going to short circuit that, and I'm going to go ahead and keep this data point. What I need you to do is look at your data table and look at your graph. And I'm going to grab a data point, even though what you would normally do is wait for these numbers to stop changing. But I'm going to short circuit that. So I apologize. I will not have super great data today. I don't know. It's like making an apology. It's like I shouldn't have to do that, but short time. If you're doing this in class, 3 to 5 minutes per water bath. Wait till those things stop changing, and then hit the keep button. Do you have a data point on your graph? Do you have a data point in your data table? Take a look. You should. You just got a point from me. Now, someone pointed out that events with entry data collection is kind of like watching grass grow. So doing that by remote could be boring. I'm going to try to make it less boring by telling some stories and stuff along the way. But the point is that, if you're not doing a whole lot of data collection, it's not bad. If we were doing, like an acid-base titration manually like this, oh my gosh, talk about getting bored. And so once again, wait 3 to 5 minutes. I can't do that. I don't have the luxury of that right now. So I'm going to let this thing go until that's room temperature water. Had it sit all night on the counter. If you're in your classroom, you might just leave out a bunch of containers of water. Cut off 2-liter bottles. Gosh, I used to make bio bottles and all kinds of things, and so they're really cheap. I'm going to keep this data point, even though I'm not quite at equilibrium, but that's all right. For our purposes today, you should now see a second point appear on your data table in about 3 or 4 seconds. Here we go. Did you get a second point? Send us a little thumbs up or something in Zoom. You know how to do that? The little reactions thing at the bottom. Okay, you probably do, or your students do. All right. All right, let me get these water baths out of the way. One more water bath and we're going to call it good. Should do 5, but yeah, we don't have time. I want to do the other experiment. I want to do a couple other experiments too, give you some good stuff here. So there we go. Warm water bath. Power tip: with this size syringe for the second experiment I'm about to do for the Charles Law experiment, anything over 30 degrees, you're going to run out of syringe, and you'll see what I'm talking about in just a minute. So there we go. It's pretty close to, you can see the temperature is going up, but still kind of slowly. Once again, I have to make an apology here, but I'm going to grab that point and we're going to call that good. Here we go. Sometimes sensors will fluctuate, and the averaging is really good for that when sensors are fluctuating. I'm going to make my teacher screen a little larger here, and I'm going to stop collecting. So look at your copy of graphical analysis. At the top, it probably says collecting, and I'm going to stop collecting. So I just stopped. Okay. Now, if at this point you are on your own, right? And so the most common thing that teachers would do, I'm going to turn off everything but the graph. This will not show up on what I'm about to do. Is not going to work on your device. You're going to have to do this yourself if you want to. Okay, so if I switch over and show you my iPad, I'm going to turn off the data table, and I'm going to turn off the meters because I don't need them right now. But notice on the iPad, some things changed, some things didn't. You're on your own. You got to do your own adjusting here. So to change those, it's this view options up here. Tap in there and you can turn things on and off at will. Most common thing you want is you want your students to establish a relationship between pressure and temperature. So we would try to fit a curve, bottom left corner. We tap on the graph tools icon. If you want to follow along, you're welcome to do that. Now you have to do this on your own. You're not going to get anything from me. Let's fit a curve to that, and let's see if pressure is directly proportional to temperature. And so if it is, then it would be a linear fit. Notice that you can try all kinds of other fits if you want. And so I'm going to hit that. Oh my gosh, I got almost 3 nines correlation. Considering I wasn't waiting long enough, that isn't too horrible. All right, bonus points, kinetic molecular theory. If the temperature drops, pardon me, I said this wrong. If the pressure drops to the point where the molecules are no longer exerting pressure on the sides of the container, what is the temperature? Well, this is very easy to determine. What we're going to do is we're going to swap the axes. We're going to make pressure on the y-axis, the x-axis, and we're going to put temperature on the y-axis, and we're going to look for the y-intercept. So tap on the x-axis first, change that to pressure, tap on the y-axis, change that to temperature, and let's do another curve fit, and let's take a look and see what the y-intercept is and see if you recognize that number. Okay. Yeah, -238, should have been -273. I was off by I can't do the math in my head, less than 40 degrees, so about 15%. I have been known to be like, I did a workshop with some teachers in Texas last week and I got negative 269. I could have been by chance, but it was kind of fun to get that value. So your students can determine a value for absolute zero. If you have more data points, take longer. All right. If you have any questions, throw them at Melissa. Otherwise, I'm going to go to Charles' law. And so the neat thing is that I don't have to change much of anything in order to do Charles' law. By the way, I'm about to start a new experiment. If you like this and want to keep a record of it, go to the Untitled menu and save it. Otherwise, we're going to start a new experiment and you're going to lose it. So be aware of that. I'm about to start a new experiment. So if you like this, you need to save it. If you don't do that and you want to join the experiment later, you'll need to put that code in again, and I'll share that code with you if you need it. But anyway, I'm going to start a new experiment. Charles' law. Back in the day when I first started teaching, I started teaching in the early 80s. We used to do Charles' law. Okay, don't hate me. We used to do it with mercury and capillary tubes. And yeah. And so, when Don Boltz came up with this procedure for doing Charles' law, oh my gosh, it just blew my mind. And so let me show you how this works, because it is really slick. Okay, so I'm going to join a new experiment on my iPad, and so it's you can see that it's getting the data from me. But here's the plan, and let me show you that this is really cool. Okay, I'm going to take this flask and put it at. By the way, the last experiment, the order of the water baths doesn't matter. This experiment, it does. You need to start with the lowest pressure. Pardon me, the lowest temperature water bath. Okay, so I'm going to put this in the lowest temperature water bath, give that a chance to equilibrate. Because if you think about it, Charles' law, what's the relationship between volume and temperature? Well, that means we need to keep the pressure constant. Hey, Noose, how are you going to keep the pressure constant? Hey, this is the tricky part that is super cool. Okay, so we need to change the data collection again. Time, no good. We need an events with entry, but we need to change this to a slightly different way of events with entry. We're going to manipulate the volume of the syringe. So that we're going to have to enter into the system. Okay, the system will measure the pressure and temperature, and the tricky part is going to be for us to keep the pressure constant. So what I'm going to do, and you might want to do this too, is turn on your meters. Okay, let me check my iPad. Okay, turn on my meters. Turn on my data table. There we go. There's my iPad. So your setup should look similar to my iPad there. And here's the plan. Going to start collecting data. Let me get the camera up so you can see what I'm doing. And actually, I'm not doing anything. This is sitting in the water bath, real cold, negative. I got some salt in there in case you were curious what's going on here. And there's the pressure. Now, here's the important thing. Take note of that number for the pressure, because we need to know that for the rest of the experiment. So I'm going to write that down. 89.8 kPa, right there. Okay, that's going to be the pressure that we're going to need to keep constant, and I'll show you how in a minute. Let me grab this point, and the system says volume. Well, this could be the volume added. This could also be the total volume of the system. For our purposes today, it's going to be the total volume of the system, which is 145 milliliters. How do I know that? In the files that I shared with you in the shared data folder, there is a pre-lab for students to determine the volume of the system. How do they do that? Well, it's up to them. That's why I wrote the pre-lab, but the idea is they have to figure out the volume of the gas. We don't need this water bath. Let me change it to the next one so you can see what I'm talking about. There's volume in the flask. There's also volume in this tube. And so what I had the students do is determine a method to find that volume. And so I'll tell you the answer, but you may or may not want to share this with your students. If you look at the pre-lab picture, there's a picture in the pre-lab, there's a balance shown. And so the idea is weigh everything. So weigh the flask with the stopper and the tubing, and then fill it with water, fill everything with water and weigh it again. And of course, water density being 1, then you can make a pretty close assumption that the volume is equal to the mass. So here's the trick. Remember 89.8, look at the pressure on your meter on your device, right? On your device, it should be the same as mine, right? So notice that the pressure is 98. We no, we don't want 98. We want 89. Oh, open the valve and withdraw the syringe. And if someone could shout out when this says 89.8, that would be super helpful so I don't have to keep looking over my shoulder.
Keep going, Noose. A little bit more. You're at 91. 90. Okay, can stop.
That's probably as good as it's going to get,
Yeah.
right? I mean, it's like, so
good.
Close the valve, okay, and it should hold it. That's pretty close. I mean, I'm off by 0.2 kPa. I hope you'll give me that with all the error that I've had today. Now, pressure is constant. We've got that. We've got the temperature. And now let's click on keep. And now what's the volume? Well, it's the 145 plus read the syringe. So the syringe 14.8. So, okay, I got to do the math. 145 plus 15 would be 155, 160. So it's 159.8. Now, what you could do is you could have your students put in the volume added to the system to keep the pressure constant, and then you could do a calculated column and have them just add in the volume of the system that was determined in the pre-lab. And so that's another way to use the calculated column option that's built into graphical analysis. So here's the thing about this water bath. If you're going to use the syringe that comes with the Vernier pressure sensor, then this water bath cannot be much over 30 degrees because you're going to run out of syringe. Okay. So if you want to do that, these are dirt cheap, a couple of bucks at the ag supply store. I got this one on Amazon. This is a 60. Okay. And so if you're going to do this experiment, you want to use a higher temperature water bath, you're going to need a bigger syringe. So, I mean, they're just lure lock. You just got to be careful when you buy larger syringes. If you're going to use them with our stuff, they have to have that lure lock connector so that you can switch it on there. But that will give you a much larger volume of gas. So once again, I need to open the valve. Hopefully I won't run out of syringe here. I need to get it to 89.8. Close. All right, I think that's about it. Close the valve. And I am just a little over. I can do a little guesstimating here, but I'm at about 22 milliliters. So a little bit of guesstimating action here. Let's keep the value. 22 plus 145, 160, 55, 165 plus 2 more, 167. Okay, here we go. All right, you should have 3 data points on your graph. You should have 3 data points in your data table. I'm going to stop collecting data. So for your students' sake then, of course, your students would see that. Notice there's no collecting at the top. So what are we going to do? Well, we're going to try to find a relationship here. And once again, I apologize. You know, I keep apologizing. Maybe I should stop doing that. Not horrible. 2 nines correlation, so it's not too bad on the linear plot there. But notice you have to do that yourself. Okay, so I'm doing it on my iPad now. Okay, so even though the students get the raw data, they have to do the analysis on their own. So that's the way Graphical Analysis Pro is set up. Okay, I've got just enough time for a kinetics experiment. Does anyone have a question that they need to ask? Melissa, is there anything I need to address?
No, I don't think so. We haven't had too many questions
Okay.
about the experiment itself. It looks like most people have been able to connect. I was able to connect. I've been doing it along with you. So I haven't heard too much about people not being able to connect, but let us know in the chat or in the Q&A. And yeah, but otherwise just really good positive feedback.
Excellent. I'm glad to hear that. All right, folks, new experiment. If you like this and you want to keep it, yeah, I mean, you could do, by the way, you could do the same thing, right? Go to change the axes. If you want to do a you know, an absolute zero, I don't have a lot of confidence with this one, but what the heck? Let's try it. What's the temperature when the volume is 0? Oh, okay, that's actually, I have this backwards. Oh, I lost points. I've got the independent variable on the y-axis. Oh man, I just lost points in my lab report. Anyway, in that fit, right? The y-intercept. Look at that. Oh, that was actually better than the last time. Oh my gosh. Wasn't the last one like -238? This time I got -241. That's like, you know, that's definitely right around what, 15%, maybe a little less. Wow, it's called luck with 3 data points. But anyway, if you want to keep that, make sure you go to save to keep it. But I'm about to start a new experiment. What I'm going to do is I'm going to do the classic crystal violet experiment, but I'm going to use blue food dye. Okay, so just the stuff from the grocery store, this stuff. Okay, and I'm going to use bleach. And honestly, folks, crystal violet's not that expensive, but if you want to just use stuff you can get from the grocery store, this will work really well for this particular experiment. And I'm going to use the Vernier colorimeter for this. Okay, could absolutely be done on a SpectraViz, but yeah, it's nice to be able to do a little more advanced, say, AP chemistry level experiment on a device that doesn't quite cost as much. So what I'm going to do is I'm going to take some 100 milliliters of water, and I'm going to put 1 drop of blue food color in there. And by the way, all these instructions are in the shared folder, so don't worry too much about that. Now, in the instructions that I shared with you all, there is an activity. It's actually the first part of the activity. I took Jack Randall wrote this a long time ago, and I changed it slightly so the students can discover the wavelength for themselves. I'm not going to do that right now because it's another events with entry thing, and you've seen that already. But it is in the instructions for this experiment, and so you can see how to do that. Have the students, if you're not familiar with the Vernier colorimeter, it has 4 wavelengths. We have a blue solution. Which wavelength would be the best one to use? You can have the students actually discover that for themselves, why you would use one LED over the other. But just for the sake of time, I'm not going to do that. Okay, I'm going to skip that part, but I did put it in there. I tested it. It works really well. We don't need temperature and pressure. Just get rid of those too. Okay, let's get rid of those. So on graphical analysis, to get rid of a sensor you don't need or to add a new one, which is what I'm about to do, little doodad on the bottom right looks like a sensor. If I tap on that, I can disconnect the ones we don't need. We don't need temperature and we don't need pressure right now. Let's find the colorimeter, COL. I'll bet that's the colorimeter right there. And so theoretically, the light on the colorimeter should be flashing green. Yes, it is. Okay, let's turn on the meter. You can follow along if you want on your end. Okay, once again, notice that it's time-based. This is okay this time. We're doing a kinetics experiment. Time-based is exactly what we want. However, I've discovered with straight up bleach and 1 drop of blue food color in 100 milliliters of water that 300 minutes is way too long, and if you let it run that long, you get some weirdness in your data analysis. This is in the lab write-up. I'm going to change the time for this from 300 minutes to 300 seconds to 90 seconds. Okay, that'll be plenty for what we're going to do here. And so that's really the only adjustment we need to do. The other thing we need to do is pick a wavelength. Well, like I said, the first half of the activity in the shared folder, students go through all the wavelengths with the blue food dye, and they determine which one has the most absorbance. And had we done that, we would notice it would be the 635 nanometer red LED. Not super surprising, I hope, to teachers, but to kids it might be. Okay, why do I say that? Because I went to a store to buy not a grow light. What was it? Yeah, maybe it was a grow light. And this kid was trying to tell me that I needed a green grow light for, and it's like, oh, really? Anyway, so what you do is like any spectrometer, I just put um, a blank in there. Blank is the solvent, in this case, water. And the cuvettes, you got to be careful. The cuvettes are fluted on two sides and they're clear on the other. So got to be careful you line those up in there so the light path is correct. And then what we're after here is we're after the meter to read 0. It's reading 0 now, but I always tell folks in workshops, good spectrophotometry hygiene, recalibrate the sensor. So the cal button is flashing on my spectrometer, or pardon me, on my colorimeter, and notice the absorbance is 0. So that's good. That's ready. And I've got it on the 635 nanometers, which, like I said, the students would discover for themselves. Now, let's set up the experiment, because we are very close. I need some blue food dye in one test tube. So let me turn off the stirrer here, put some blue food dye in one test tube, and then I'm going to put about an equal amount of bleach in the other, and that bleach bottle is just too big to handle. So let me get a beaker here. And let's get some bleach in there. It'll be a little easier to handle. Yes, I have my goggles on. I had a teacher this morning at a workshop. They do. So you wear goggles? And she caught me, man. I was doing an acid-base titration and I had my glasses on instead of my goggles. I couldn't believe how embarrassing that was. Yeah, because I'm pretty good about wearing them, but oh my gosh, it was like, all right. So there's about equal volumes of each. What we're going to do is we're going to take a barrel pipette and put some blue food dye. What I'm going to do is squeeze the pipette, kind of, I'm old school and I tend to reuse stuff. And so let me rinse that pipette just to make sure. And what we're going to do is I'm going to fill one cuvette about halfway, a little less than halfway, with blue food color. Okay. Now, some of you purists may, when you look at the absorbance of that blue food dye, when you do the first part of the experiment, you may notice that the absorbance is higher than 1. If we were doing a Beer's law experiment, that would be an issue. Because Beer's law gets all wacky above 1 because it's a logarithmic relationship between transmittance and absorbance. And so, but for this experiment, we have to cheat a little because we're going to mix these two together, which is going to be an immediate dilution. And so that's going to be an issue. And the reaction is pretty fast. And so that's also an issue. So what we're going to do, let me get these over here. I'm going to now here's the tricky part. This says this in the lab procedure. I'm going to put the bleach into the blue food dye. I'm going to put that into the colorimeter, going to watch the meter on the screen to see how high it gets. And then when it gets to the highest value, I'm going to start collecting data. So here we go. I'm going to shut up while I'm doing that so I don't make a mess. Here we go. Are you getting data? Give us a thumbs up. To get data, I'd like to see a thumbs up in Zoom. So what's going on? Oh, what's going on, Deuce? Why did you have the rest of these be? Okay, because you can pour them together and then have the students get a nice visual. In our Crystal Violet lab, we have them do it like that. We have them, mix it in test tubes and then pour that into the cuvette. For the sake of time, I did it with the cuvettes. But the nice thing is, if you do it that way, then the students can actually get a visual. What's going on inside here? Because it's kind of black boxy, right? Because they can't really see. But here you can hold this against a white surface and you get a little feel for, oh, it looks like here's the original solution, right? So we can look at the original solution and say, oh, definitely some kind of reactions going on. The blue color is going away. And so and then of course, in terms of the data, we look at the data and go, oh, that's interesting, the shape that's taking. And so let's let that go until the time runs out, and then we'll do the analysis together. I'll help you do it together. Oh, where's my iPad? Forgot about my iPad. Oh, I'm a late student. I was asleep. I just woke up. Oh, Mr. Hism, I need the data. All right. There you go. Grudgingly, I'll give you the data. Okay. So stopped here. Now you're on your own. Well, not completely. What I need you to, those of you that teach this, you know that the relationship, we're looking for a rate law. We want to know if this is zero order, first order, or second order with respect to the blue food color, since the bleach is much, much higher concentration. So what we're going to do is we're going to turn on a data table. Top right, the box in the boxes, tap on that, turn on your data table. Okay, oh, let me do that on my iPad. Data table. Okay, now what first, we know it's not zero order, because if we look at that, if it was zero order, this would be a straight line. So that's not true. So let's see if it's first order. So what we need to do, and I'm going to make my teacher screen larger so you guys can see, because you can follow along on your end. I'm going to tap where it says absorbance, and I'm going to add a calculated column. If you do integrated rate laws, you know that if it's first order with respect to a reactant, then the first derivative of that concentration should be linear. So let's see if we have that. Wasn't on the test this year. I noticed that when I looked at the AP free response questions derivative, there wasn't a question specifically like this year, although it has been on the past. Was there a Beer's law question on the test this year? I know the answer. The answer is yes. So you're going to do a calculated column. If you weren't following along, you click on the three dots next to absorbance, add calculated column. I'm calling my calculated column first derivative. You can call it first if you want. Down here under expression, just tap on insert expression, and there is the calculus there for first derivative. So we'll do that. You want to make sure that it's finding the first derivative of the absorbance. We'll talk about concentrations here in a bit. We'll tap on apply. Okay. Oh, Noose, that's just boring. It didn't change anything. Tap on the y-axis label. Turn on the first derivative and turn off the absorbance. What the heck? What did I do wrong, Melissa? Did I do something wrong here? It's usually a negative slope, so that's why I'm wondering what I did wrong here.
I'm looking.
I must have done something wacky here. I know those first points were a little high, but it's like usually a negative slope. What went wrong here?
Yeah, the scale is really.
It's really strange. That's a
tiny.
strange scale. It won't automatically. Huh. Did I select? Okay, I'm gonna delete that.
Go back to your equation and double check it.
Yeah, let's go check it. Did I do it? I might have done it backwards. So, you know, one option is delete this column. You could just delete it. But the other thing, what Melissa was saying, if we go in the column options, I might have it backwards here. I don't think I do though, do I? I don't think this is backwards, but I'm going to change it anyway, just to see. Yeah, that's more like what we were expecting. It's usually a lot more linear than that. In the data, there's a shared data file in the folder, and it's way more linear than that. So I'm not sure what I did wrong here, because this is not so great. It's pretty crummy. Well, let's do the second derivative and see if that's better. I don't know what's going on here though. I don't know if it's these points up here. Tell you what, maybe you want to massage your data a little bit. Do you allow your students to massage data? Maybe not. They would have to justify why they were doing that. I'm not real thrilled with that initial data that's above 1. So I'm going to take this data right here. So the way you do that, if you want to just include a certain part of the data, but not everything. So I'm going to pick that part of the data by clicking and dragging. And I'm going to do another calculated column, and it will do it just on the part that I selected. I'm just a little surprised because I've done this many times, and it's almost always come out perfect. And so derivative. So I'm kind of curious why it's being, oh, I'm an idiot. Why am I taking the first derivative? Because this morning I did an acid-base titration. I don't want first derivative, integrated rate law. I want the log of the concentration. Sorry about that. I did a workshop for some teachers this morning, and we were titrating an acid and a base, and that's why I've had first derivative on my brain.
I
Sorry
was
about
about
that.
to ask. I was like, I'm not
Yeah.
sure where he's going with this derivative thing,
I
but
was like a
I
bonehead,
get to see
right?
all the time. I was just gonna see what you were doing with it.
Yeah, it's like what the heck, oh geepers, why is this not showing now? First derivative, I've got the first derivative showing. Let's see here. This has been really not so great. I mean, I don't know what I did, if I ruined something here. Time is okay. First derivative is on, but for some reason it's saying y-axis. Did I find a bug here? I don't know. That's pretty unusual. Okay, let's tell you what, I'm going to do two graphs. So this is a kind of a cool thing in graphical analysis. You can turn on more than one graph. Okay, and I can have the original graph at the top. So there's my absorbance versus time at the top. And then I can have my derivative down here, and I'm curious to see, there it is. I don't know what was going on having them both in the same graph. It was being kind of wacky. Notice it is very nice. This is what I was expecting. So, if the food color is first order with respect to, pardon me, if the rate is first order with respect to food color, then this should come out to be a straight line. And you can see that's, like I said, I usually get good data. Notice 4 nines correlation. So that's what threw me off. Now, what if, if you might want your students to complete the circle, right? Okay, what if it's second order? Pretty common thing. So cross my fingers, throw some salt. Let's see if I can get that to work. Second order is going to be inverse concentration. So what I'm going to do is tap on the 3 dots next to absorbance, add another calculated column. This one will be second order. Or what am I saying? Instead of second order, today it's like, man, we're going to call this one, I'm sorry, inverse concentration, or in this case, it'll be inverse absorbance. We can talk about how to get the concentration in a minute. So which relationship? Well, of course, it's going to be A over X. I don't know. Sorry about that. I apologize for the first derivative crap. It was like I did a workshop real early this morning before I had my coffee. And any of you know me, coffee is really important. So let's turn on the inverse up here and let's look at the graph of inverse. Wow, that first graph is wacky. For some reason, that first graph is not super great. All right, let's look at the second one. I may have found some kind of a little weird thing. Anyway, here we go. Let's turn the absorbance back on the first graph. There we go. And so you can see, not linear. You can have 3 graphs. So neat thing is, with kinetic study like this, you can have the students do 0 order. You can have them do the I still called it first derivative, didn't I? I am just an idiot. Let's do, this would be ln absorbance. I apologize. So I could have the log of the absorbance here, and I could have the inverse of the absorbance here. So your students could create a report that has all of the plots in graphical analysis. These are all exportable. You can rename you can put names, titles on each one. You can export this. And as you can tell, the data is not that horrible, but my graphs were sort of acting wacky. But kids could take this graph and they could export. They can make a PDF too of the graphs, right from graphical analysis if you want them to create reports and things like that. Questions before we kind of getting close to the end here? Anybody have any questions, concerns? Did you see how I screwed up? It's okay.
No one has had any questions so far.
It's my birthday. Don't I get to screw up?
Yes, you definitely do.
Okay, all right. Okay, it's one of those special birthdays too. Those of you who know me well, you can contact me and we can talk about it. Anyway, and so notice that here is the my iPad. Okay, so you can see some things going on there too. Now, as far as graphical analysis goes, would you use it in your classroom, particularly for teaching? Remotely, or maybe, like I said, some sort of hybrid where kids might be at home, or you might have groups working together, and you might have one group that transmits the data to other people. we have a free 30-day trial. Go on our website at Graphical Analysis Pro, and you can sign up for that. The way the subscriptions work for graphical analysis is they go through the following years all the way through June. I think it says on the website July 1st. And so it's a $199 for over 500 students, $99 a year for under 500 students. Now, do you need graphical analysis to collect data with Vernier? No, you need the free version, but the pro, what else do I get for my $99, Noose? Check this out. You have this, by the way. You can try it if you want to follow along. Let's start a new experiment. Okay, and check out this button that says See Experiments. Melissa did a lot of work here for chemistry. I'm going to change the filter to chemistry. You can also pick by our books. If you use our lab manuals, there's specific experiments from chem and whatever. But what about the crystal violet one we just did? Oh, isn't that in here? Oh, look, there it is. Let's take a look at it. So what Melissa did is she did this experiment with crystal violet and actually collected data with this. And so you can see the data over here. You can also synchronize the data. There is a way in graphical analysis, this is all the synchronization business up here. So you can actually have it so that the data that you collect is synchronized to a video. Wouldn't this be a great resource for a student that was, say, absent? Okay, or just needed a review, because it's still just the data. Students have to do all the analysis. They have to come to their own conclusions. So you still have to do that. So built into Graphical Analysis Pro are a number of experiments with data. We have lots of old Logger Pro teachers that, I really like the ability to open up some files that were ready to go. We went further and we actually set these up so that, not only do they have, here's Boyle's Law if you're a gas law person, but they have data and videos. Hey, Noose, what if my students collect data on their own? Could they put it in graphical analysis? Absolutely. Let me go grab a data file that I've got. You may have one on your computer. If you take a data file, maybe you collected some data in class, and so you want to then add a video to that. So I could have like some acid-base titration, say, and let me get the. Definitely got some weirdnesses going on. There's my acid-base titration. And wouldn't it be nice if I could add a video to that? I go to video under the view options. And now, unfortunately, I don't have a great video for this one already made, but you can take a video with your phone or with anything that has that has the ability to take a video, and then you can add that to graphical analysis. So you can have, this is my students, those of you might do the brass lab may be familiar with it. So you could create your own data sets with video, or you could have your students collect data, take a video of themselves, and add that to the graphical analysis file. And so that's also a feature of Graphical Analysis Pro. Hey, Noose, what if I buy graphical analysis this year and next year I don't have graphical analysis? What happens to the data? Nothing. So if I am going to do what I do not encourage you to do. Look at my screen, don't do this. I'm going to change my copy of graphical analysis back to the free version. Okay, I'm changing mine. Notice that I have the TIE Fighter up here. I'm going to get rid of the TIE Fighter. So I'm going to get rid of it. Okay. Just put a fake code in there. And now my TIE Fighter is back to the shield. But look, the data is still here. You do not lose your data. So if a student, if for some reason you can't make Graphical Analysis Pro work, as long as you just are interested in your data, it's still there. Okay, and we're getting real close to the end. Couple of things. If you want to contact any of us in the chemistry group, it's chemistry@vernier.com. We have a chat line on our website if you want to talk to us, during business hours. We have people always available on the chat line. And so last but not least, does anyone have any questions, comments, or concerns for Melissa or I? I'm
Nothing
hearing.
has come in through the chat, but is there anything else that GA Pro has that the graphical analysis doesn't, the free version?
Remind me, Melissa, what am I, it's my birthday. I'm getting old.
Well, the custom calculated column, the custom curve fits, and the ability to do your own expressions and all that kind of stuff. It kept popping up every time you tried to add a linear fit. There was like,
Yeah.
create your own.
What happens is that when you are doing fits, and when you're doing, oh, I don't have that pro anymore, do I?
Right.
Let me make myself pro again. When you're doing fits, you have the options of doing custom fits, so you can put in your own functions. When you are doing calculated columns, what Melissa's referring to is you have the option now of putting in your own functions. And so, which is something that was in Logger Pro, and so when you have Graphical Analysis Pro, you get this option for custom expressions. So you can type in, lots of expressions. Well, I did an experiment when this first came out where I used a Wolfram Alpha calculator to get a crazy expression, and I pasted it in there, and it took it. I couldn't believe it. It was like, whoa, this is amazing. So yeah, so that's that. You're right. I forgot about that, Melissa. Thank you.
Yeah, I know. I always used those features in Logger Pro a lot. So I'm really glad that it's in Graphical Analysis Pro now.
Yeah. All right, folks, I'm going to hang out. We're going to hang out for a few more minutes. If you have any questions, want to talk to us, turn your mic on and talk to us. Otherwise, we are at 2 o'clock. Well, 2 o'clock in Pacific time, so we're at the end of the workshop. But we're going to hang out to the very end. So if you have any questions and or you just want to talk, open your mic and say hi. Otherwise, have a good rest of the day.